quick recap of yesterday, we learned basically how to detect a source. First of all, we learned what type of data do we have, right? We had a tutorial with data exploration. We learned how to detect a source, for which we need only the event list. We took a look at the IRF. Specifically, we looked, if you remember, at IRF that do not depend on the offset, and we use those to basically compute the flux. Either we computed the differential flux, so flux is a function of the energy, or we also explored a bit how to compute the integral flux and what useful quantities we can, let's say, estimate for a variable source, right? So today we will enter into a new science case, which is basically more than one source in the field of view. The field of view that we had yesterday was Crab and Markarian. And if you remember from our sky map, there was only a hotspot, right, in there. So the only active gamma ray source in that field of view, in the little patch of sky that we can observe, is just the Crab, right? So today we will check a field of view that contains two blazar sources. So it contains the blazar 1AS 1218 and 1AS 1215. Okay, so let's import the basic gamma pi stuff. No module name regions. Python 3. Okay, 1 second. It seems I'm not using the gamma pi environment. And I opened it from the wrong terminal. Here we go. Okay. Okay, very good. So we use the data store as we did yesterday to load the data from these fields of view. The data are labeled with the name of the source that is in the center of the field of view. Okay, we will see that in a moment. We will enter it into more details. So what do I mean by that? Basically, we perform the wobbling around the coordinates of 1AS 1218. Remember yesterday, we don't point directly at the source. We put the source at a certain offset such that we can estimate the signal and the background from regions with similar acceptance, right? With similar performance. And typically, we use this value of 0.4. Okay, so in principle, with this data, we could run the analysis that we did today, right? And we would obtain the spectrum of 1AS 1218. But then the thing is that in this field of view, there is another source. Look, so let's see how the field of view looks like if we try to make a count map. Okay, so basically I'm just defining the coordinates of the two sources, 1215 and 1218, and then I'm defining on region, so a small region around the source that we will use to extract the counts. And then I'm defining an exclusion region. What is an exclusion region? Well, it's nothing different from the computational point of view of the on region, right? It's a circumscribed region even with the same radius. But let's see what do we mean by that. Let's create a map. And then I made this function, this utility function, to plot directly the field of view with these two regions, okay? With a region of 0.2 degree around 1ES 1218 in red, and with a black region around 1ES 1215 that we call exclusion region. So what's the issue now? As I said, we are wobbling around 1218, no? And you can see this from this series of plot. You see, this was the wobbling where the source is at the right, let's say, from the pointing position. Then we have the other wobble where the source was at the downward, let's say, from the pointing position. Then we have yet another wobble when we have the source leftward of the pointing position, okay? And upward, okay? Not pointing at the source, we are rotating the source in the field of view, okay? All good so far, no? And for example, we can use a non-region around the source like we did yesterday, and then we place the off region symmetrically, no? In this case, I'm using 3 instead of the 1 that I used yesterday, okay? The important thing is that they are at the same distance. Okay, here, everything looks fine, right? I'm wobbling around the source. This is my own region. This is the off region. And the other source is here. So it's not let's say, messing up with my signal or with my background estimation. No? Here, the same. It's close to one of the off region, but well, it doesn't look like it's any eventual gamma ray signal from 1215 is spilling out in the off region, right? That I should use to estimate the background. But look at what happened here. In this particular configuration, the other gamma ray source is on top of one of the off regions, right? So this is a problem because now I'm estimating the background from the off regions, but here, potentially, I have another gamma ray signal. So this is not good. So what we will do is to define an exclusion region. When gamma pi performs basically the data reduction, this exclusion region will turn in a basically set of pixels, and gamma pi will exclude the off region that sits on this set of pixels. Let's say, okay, simple as that. So it will do the data extraction as we did yesterday, and then if it sees that the off region is on top of the exclusion region, this area where we say, look here, potentially there is a gamma ray source, it will not extract the background from there. I think it will actually not process the run at all, okay? Okay, and then pretty much we do the data extraction as yesterday. We have the energy axis, and then remember that the size of the on and off region, they are in the Radmax table. So basically the center of the on region, sorry, the on region is defined through a point sky region, right? Just need a point and the size of the on region with the determined from the Radmax table. And then we do this with the geometry of the sky map. Basically, we convert this exclusion region that we generated that now is basically a circle sky region, so a region object, right? We convert it with this operation in pixels, basically, in this geometry of the sky map, okay? This is a region, and this operation, it converts it in basically blacked out pixel, okay? That will be ignored. And then the trick that I did, because as I said, if gamma pi will find that the off region sits on the potential, on the exclusion region, let's say it will not process the run. So the trick that I did is to use two off region. In this case, if we use two off region, it will never happen that they overlap with the exclusion region, and thus it should be working. Are there any questions so far? So very similar to the process that we did yesterday, adding the exclusion mask, which is just a set of pixels where gamma pi doesn't have to take the background measurement, okay? Everything good? Okay, if there are no questions or complaints, let's go ahead. So as yesterday, we stack the data set. Remember, in this case, we just want to estimate the spectra of both sources in the field of view, right? So I'm not interested in run by run information, okay? I'm not interested, for example, in the temporal variation of the sources at the moment. So I'll just stack all the data together. And this is my data set stacked. As yesterday, I will use some reasonable range of energies to perform the fit. And once you define this basically mask for fitting, mask fit, gamma pi will display it with this green band in the counts, basically, when you examine the data set. Stacking, fitting mask. And then we continue. We define a power law spectral model, and we perform the fit, right? We define the spectrum, we define a sky model with the spectral model, and then we run the fit. It was really fast. Let's compute also flux points. It will not take a while like yesterday because now we have just one data set. So hopefully is quick enough. Okay, so let's plot spectrum and flux point. Okay, what I observe is if you remember the Crab Nebula spectrum yesterday, the log parabola shape was agreeing very nicely with the flux points. And here I observed that it's not the same, right? So it looks like there is some sort of break in my spectrum. Can you interpret what the disagreement between the broadband spectrum fit and the individual flux points is telling us? What did we say yesterday? I'll come back to Guillermo's question in a moment. Anyone remembers why we did compute flux points in the first place? Because when I fit when I use a broadband fit, uh, I'm assuming that the whole spectrum is described by this analytical function, right? And- But this is not certain, right? I'm making an assumption of the spectrum. So when I readjust, basically with the flux point estimation, at least as it is done in gamma pi, when I readjust the spectrum, the fit pin by pin, I can see where in which regions the fit is going differently than the single assumption that I used that I thought it was valid for the whole energy range. You see what I mean? I'm readjusting this power law bin by bin, and here it seems that it's deviating quite a lot from my assumption of a single power law, right? So what does this mean? Well, perhaps the power law is not the best spectral model, right? And what's happening is that these sources are quite far away. They have a redshift of 0.82, and the other, I think it is 0.13 or something like that. The thing is that while high energy photons, especially gamma ray, travel to Earth, um, they are absorbed by the soft light that permeates the universe. Soft meaning that goes from the, let's say, infrared, optical to UV. These soft photons interact via pair production with the gamma ray photons. Okay, so yeah, so basically they are absorbed, and we can plot the model of this absorption using gamma pi. EBL means extragalactic background light, which is the name that we give to this, let's say, soft photon field that permeates the entire universe. And here you can see the absorption factor for a distance of redshift 0.182, which is basically the redshift of 1218. Okay, so we have to take into account this in our fit. And how do we do that? Basically, we multiply the power law with this absorption model, okay? So that is literally what I'm doing here. I'm taking the spectral model that I defined as a power law, and I multiply by the absorption, and the parameter of the absorption is the redshift, okay? Fixed parameter, we're not going to fit it. That's basically what I'm doing. I'm defining a new sky model with the absorption. I'm assigning the model to the stacked dataset and reperforming a fit. And then we go and compute again flux points. Okay, and look now. Okay, so this in blue is what I obtained now. Okay, you can see that now the agreement with the broadband model that I assumed is much better with the individual flux point. You see that the flux points are exactly as before with this break in between them, but now since the absorption is producing this curvature in my spectrum, basically I can reproduce this jump, let's say this fall between the 2 points. You see? Before I could not because I had a straight line, and now I can reproduce it very well, okay? And what I can do is I can plot also the intrinsic spectrum of the source, so the actual spectrum of the source without considering absorption, okay? So if we assume that this is the EBL model that is describing the absorption, we can say that this is what we call the intrinsic flux of the source. So this is the flux in gamma ray that the source is actually emitting, and what we are observing is the absorbed flux, okay? And I think I showed here how to, yeah, basically compute these intrinsic flux points. And I just plotted the spectral model without the absorption, okay, to have the red straight line. Okay, let me go back to Guillermo's question because it remained unanswered. What Guillermo did was basically to rerun the cell with the off region and using two off regions. So I guess he did something like that. And he said, well, in some cases, there is some overlap with the sources. Why in this case is still not failing? I think it depends on how much it is overlapping. I don't know what is the criterion, the actual criterion that they use, but what I observed is that if I use three of regions in the data reduction, it will fail. I'll actually show you. Where is it? Here. So if I use number of off regions 3, it will start to tell me that found overlapping on off regions, choose less of regions. No off region found outside the exclusion region. So I don't know if it says found overlapping on off regions because when you give the exclusion region, it tries to shuffle to move around the off regions and they end up overlapping with the on. I don't know what the machinery is doing, but I think it's keeping all of the runs with the where you have that that issue of overlapping. So I don't know what exactly is doing, but I think from the error message is trying to reshuffle the position to avoid exclusion region. And maybe the issue is that if you have this case with a 3 of region, it cannot fit 3 of region excluding this one. I think this is what it's trying to do because this is at least how I interpret this message because it says overlapping on and off regions. So choose less of regions. So maybe if you give it 2 of regions, it can move them slightly to avoid the exclusion mask and everything is fine. Exactly. So you minimize the number of runs that get skipped then. Exactly. In this case, it is able to avoid the exclusion region by moving the off. And so you don't have to exclude any run. But in this case, if you say I want 3 of regions, I think what it's telling us is I cannot fit 3 of regions avoiding the exclusion mask. 3 of regions in a circle of radius 0.4 of offset. I think that's what it's telling basically. Okay. Is it clear now? Okay. Thanks a lot for the interesting question. Okay, so far so good. It's pretty much the analysis of yesterday. We just have this trouble with the exclusion region, right? Let's say we had this additional step of adding the exclusion region and the EBL model, right? But basically we didn't do anything much different. And what do we do now if instead we want to swap the role of the sources? What do we do now if we are interested in estimating the spectrum of 1215 and we don't want any interference in our signal and background estimation from 1218? What do we do now? So let's go in the other part of the notebook. So basically, we swap the roles of these two sky regions, right? Now, one is 1218. Yes? Did someone raise a hand? I saw a hand appearing. No, okay, sorry. Okay, so now we have a sky region with 1215 coordinates, which is what we are interested in, and we have to define the region around 1218 as exclusion region, right? So let's do what we did before. Let's basically make a plot of the situation now, okay? So now 1215 is red because it's my source, And then 1218 is black because it's the region from which I don't want gamma rays, okay? And as you can see, this is one of the runs. I think it's the same for runs as before. So here I can put my 3 off regions without problem, without overlaps. Also here not. I have 1218 sitting on one of my wobbles. And here as well, I can do that without problem. I have a question for you. Why does the offset change? Because you see something very different from here, no? Here, the offset remains always the same, no? The circle around which I put my on and off regions is always the same. Why does, in this case, change the radius of the circle, right? We see here is something of the order of a degree, no? A degree here is something less than a degree. Here is something much smaller, 0.4 maybe. And here is again 0. More than 0.4, 0.5. So why does the radius around which I'm placing the on and off region changes now when I consider the other source? Any hint? Exactly. Very good, Elisa. So Elisa said that we were basically wobbling around 1218, and it's what I still see here, right? You can see that I'm doing the wobble observation with 1218. You see it now, it's 0.4 degree rightward of the pointing. Now it's 0.4 degree downward. Now it's 0.4 leftward. 0.4 upward, right? I'm wobbling, I'm doing my pointing around 1218, but 1218 sits a different position in the field of view, okay? Because of that, because I'm doing my pointing around 1218. And yeah, 1215 has its fixed position with respect to 1218, so it will appear in different part of the camera. If you see, they're always in the same relative positions with respect to each other. Okay. And here, basically, we have a problem because let's say we have something else that we have introduced, we have to introduce with respect to yesterday, no? Because if you remember, when we did the data exploration yesterday, basically we had IRF only at 0.4 degree, right? Because I said most of our observation are at 0.4 degree. Let's see if I can plot again directly the IRF. Yeah, my response, the response of the system is basically known as simulated and known as 0.4 degree because most of my observations are done there. But this will not work in this case, right? Because in one run, my source is at 0.3, etc., etc. Actually, I computed the offsets. So in some runs, the source will be at 37 degree from the 0.37 degree from the center. So here, maybe it would be still okay to use this because this is at a response valid at 0.4 degree offset from the camera center. But then for the other runs, sometimes the source is at 0.83, sometimes the source is at 0.9, sometimes it's at 1.1. So I definitely need a response as a function of all the offset, right? And this is what we actually implemented is in this data. Okay, you can see here that the effective area is really a function of the offset. Okay, it's not simply merely simulated at 0.4 degree. And then basically what you are seeing here in yesterday data is a single beam in offset, right? It's a beam centered around 0.4 of 0.1 width. And what we have today is beams of 0.25 width, right? And then we have the effective area as a function, really as a function of the offset. And then what I do, and what basically gamma pi does under the hood when it does the gamma, basically the data reduction, is to automatically pick up the IRF at the proper offset for each of the observational run, which is what I did here. I basically took all the offset and I computed the effective area at the different offset. I use the term computed because basically we store a table in our files and basically gamma pi interpolates it. Okay? So far, so good? Okay, so really a different type of data, right? Because here I have there is really the response as a function of the offset. No other way I could compute the spectrum of 1215. Maybe if I use the single offset IRF, I could get right the spectrum for this run, the run for which it's at 0.4. I think it's this one, but the other one will be completely messed up, the estimation of the spectrum. Okay, so as I said, gamma pi will take care of that. So when it will loop through the observation, when we do the data set, it will fill the array of on and off counts as we did yesterday, using the on and off regions and taking into account not to pick up the background from the exclusion region. And then it will automatically compute the IRF at the respective offset of each observation. We stack again the data set. We're not interested in the run by run information. And let's basically repeat the fit. This source has a redshift of 0.13. So what I did was I defined a new power law, a new absorption model, and I multiplied them, okay? I put them in a sky model and I run the fit. I assign this model to 1215. Let's also compute flux points. Okay, and then basically the last plot of the tutorial is yeah, to plot both sources and to plot both the absorbed spectra, so the spectrum keeping into account the absorption, and the intrinsic spectrum. So the same, the individual spectra, but removing the absorption factor. Okay, so you can see in light colors the, let's say, intrinsic spectra of the sources, the actual spectra of the sources, if we are right on our assumption of the EBL model. Okay. And then I propose to save the results to disk, because actually in the next tutorial with Marcel, you will reperform the same analysis, but with another technique that is called 3D data analysis. And then we will make a comparison between these results. Okay, in principle, I'm done. Are there questions? Okay, then if you want, we can try to do the exercise of fitting 1218 with a log parabola absorbed by the EBL. And let's check it. Do we have a way of checking if the fit is better than with the simple power law? So let's try to do a bit this exercise, and then at 10 we switch to the other tutorials. So I'll leave you some time, and yeah, just speak up or write if you have any issues. I think it should be quite easy, no? We have all the ingredients, we have the data sets, we have the absorption model already. Any issues? Did someone already get some results? And especially, do we have any hint already or on how to answer if the fit really improved or not? If you remember, yesterday we examined which quantity and in particular which attribute of the data set we could take a look at to see if the fit is improving or worsening. I'm just asking if the fit improved. Then we can also discuss if we have time, but maybe not, if it improved significantly or not. I start to sketch out the solution. I think we did not import the log parabola. No, so we should do it. Gamma pi dot modulus import. Then where did we place the reference energy? 20. Okay. Any spectra? Just for completeness, I had hiccup. Sarah. So if you had a similar problem to to the one that Sarah is reporting, you can use kind of yeah, you can specify uh, basically the gamma pi version and the Conda Forge channel. Continue drafting the solution. And, yeah, one is 1218 plus 304. We have to assign it. So we have data sets. We can just do it on the stacked data set. Data set of models equal a LP absorb model. And then we just run the fit again. Fit dot run sets was I think this should work. It's not parabola spectral model. Okay, so it worked. Let's examine the two spectra. So let's plot the absorbed spectra. So big. Let's plot the absorbed power law first. So it should be absorbed spectral model 1218. The plot, and I think we have to put in an energy range. Did we define it before? No, we never did. So let's just define an energy range. Let's plot from 80 GeV to 20 GeV, maybe to 10 GeV. Plot. Let's give it plot the error as well. I think we have to specify the SCD type. We square the ND and then we give it a label. We square the ND and then label. So power law. Let's plot the error as well. And then let's do the same for the log parabola. Okay. I'm not using correctly the plot function. Note the first argument is energy bounds, and X is the second one. Well, I have defined this plot gamma pi SCD function that works with allows you to plot flux points and flux model at once, but here I'm just interested in the broadband flux model. Okay, I don't want the label of this thing of the error, and I didn't do plot error. The log parabola, we give a label absorbed, absorbed LP. See now. Okay, it doesn't change the color of the pens, maybe it's face color. Okay, so I don't know if you already obtained this type of plot. What can we observe? That low energy is pretty much the same, the fit with the absorbed power law log parabola, but we start to have much more uncertainty at the highest energies for the log parabola. So we are getting a slightly different fit, but at the price of a larger uncertainty of the parameter, right? The fact that this band is larger means that the error on the log parabola parameters is larger than the error on the spectral model parameters, no? And I think it's also what we can see if we just plot the model. I think it's parameters two table, parameters two table. So for the power law model, we have an index of 2 and an error of 0.5, more or less. No, actually 0.05. And instead for our log parabola, we have something similar, 2.3 and 0.05. The amplitude is almost the same. Here it's 3.8, 10 to the minus 10, and here it's 4, 10 to the minus 10. And the errors are also compatible, but here we introduced beta, another parameter with its own uncertainty. And if you see here, the error on the beta is quite large, right? It's the same order of magnitude of the no? The error is almost the same as the quantity, no? So this is already indication that perhaps complicating the model it's not so useful in this case, no? Okay. And if you remember, we have also this stat sum quantity, no? That we can use to check whether whether the fit improved or not. So we can perhaps go back when we did the fit with the with the absorbed power law. Total statistics for that fit, so minus to the log of the likelihood, is 19, right? With the absorbed power law. And with the log parabola we got 18.36. So it improved by 1, right? So perhaps it's maybe not such a good improvement, no? So we can see it already from the value of the likelihood. There's a more quantitative way to do it, which is basically the ratio between the difference actually between two log likelihood, or the log of a ratio of likelihood is distributed as a chi-square with a 1 degree of freedom, no? As we saw yesterday. So in principle, we could compare these two and quantitatively estimate, no, if the improvement of the fit is significant or not. But I can already see that it's not really significant, right? The statistic diminished by 1, and I introduced another parameter at the price of having an error that is comparable to the parameter, no? And this is why I see this bigger error band, no? So let's just plot the intrinsic model, and then I leave the floor to Marcel. Just out of curiosity, let's plot the intrinsic. So I think the the normal log parabola was just spectral model, intrinsic power law. Let's see. Yes, indeed. And then for this one, we have a LP spectrum model. So the intrinsic let's plot also the error, and this would be intrinsic log parabola. Yeah, as you can see, it's not really so different from the power law, and the region in which they deviate, it has huge uncertainties, okay? So really in this case, fitting with the log parabola doesn't provide any advantage. Okay, and again, the difference within the two is that the lower ones do take into account the BL absorption, and the one higher to are, let's say, do not have this absorption factor. So if you don't have any questions, I think we can go ahead with the very interesting 3D tutorial by Marcel. Any final question? Okay, then I'll stop sharing.
All right, then I think I will just. Can you allow me to share, Cosimo?
Yes. Let me understand first how to stop sharing
Okay,
myself.
sure.
I think I allowed it because I'm the host. Is it possible now?
Okay. Yes. Yes.
Okay, I
Okay.
guess you're still seeing my screen, no?
Yep. But
Yes. Okay. How do I stop it? Oof. I lost there is usually the panel with the meeting controls, but here it is. Okay, sorry.
okay, I hope you can see my screen now.
Yes.
Um,
Good.
Okay, perfect. Yeah, my name is Marcel Strzys, and I'm currently a project assistant professor here at the Institute for Cosmic Ray Research at the University of Tokyo. And yeah, it's a kind of like pleasure to introduce here the 3D analysis case to you within this school, which kind of like for this type of source, one could argue whether it is needed, but I think it is a very interesting comparison, and at the same time, is a skill that might be useful for you in certain analysis cases. Particularly if you search for a source in the field of view where you don't know the source localization yet. So some transient source, for example, or if you have some extended objects, or finally, even if you have two sources, 2-point sources, sometimes you may have cases where source regions overlap. And for all those cases, a 3D analysis might be useful. Or in the case of this source here, it allows you to basically extract the spectra of both sources in one step. It is meant as a complementary method here, not to substitute the 1D analysis, but to complement it here. So please interrupt me kind of like any time. I have the chat here open, so I should see your questions. If not, then please also feel free to just interrupt me. The beginning of this notebook here, kind of like similar as what you have seen with the previous one, basically loading a lot of these packages that are needed here from either AstroPy or GammaPy, and you see that from GammaPy there are a lot of more these so-called estimators and makers, which we will then use out throughout this notebook. The data files are basically the similar files that you used before, just with one addition. that a background layer was added here. So this data here contain a background model, and they contain the full enclosure IIFs. So basically, that means they contain the IIFs for the entire field of view. So you have a 3D models. Then you see here that this notebook contains a queue, kind of like a fix here for the background. You can kind of like, this is more like a detail which you can ignore. It's basically the alignment of the right ascension axis in the background model here, which is slightly deviating from what the newer versions of Gamma Pi expect. So this is just like a small fix. And if you see some issues with older versions of Gamma Pi, so using it before 1.3, Gamma Pi 1.3, then you actually need to switch off this option here. Now we can actually have a look. Once the data are loaded, we can have a look at what is contained in the data, and this is usually like the first thing to check whether what we have there is reasonable. So now you see the effective area like in 3D, basically field of view offset to the energy. However, what is important here for this data, what is the big difference, is the background model that you see here. And as you would expect it for Cherenkov telescope, the background is higher in the central part of the camera and at lower energies, and then kind of like fades out towards the outer parts of the camera and higher energies. Okay, so then kind of like the usual things that we need for like in order to perform analysis. So basically the settings of where we would like the data to be extracted by Gamma Pi, because Gamma Pi is then constructing our data sets out of these observation files. And it will do it within certain ranges that we set. So we define our energy axis. So, and the minimum and maximum energy and the binnings that we want in true and in estimated energy. And the spatial binning, which we would like to have for our sky maps later on, because we are also going to create some sky maps and some detection plots. And usually here for the binning in spatial coordinates, if you want some quicker analysis, you may use a coarser binning. However, if you want the best possible resolution, then it makes sense to put your size of the 1 pixel to something like half of your 39% containment radius of your PSF. Thereby you are getting close to the so-called Nyquist limit, which is your maximum resolution that you can have with your instrument. And for MAGIC, we are at the highest energy, somewhere like 0.5, so 0.05 degrees. So by putting it to a bit less than half, we get the optimal resolution. And then we can create what Gamma Pi expect this world, this geom object, which contains all the information about this world coordinate system that is used in the analysis. Okay. Then this you may also be part of the, I think the previous notebook is that Gamma Pi then has so-called dataset makers. So basically, these are the tools which will extract the information from the observation file and will create data objects out of this with which you then can run the analysis. And here we have map dataset makers. So because we are going to run a 3D analysis, so the two spatial bins defining the maps, and then in terms of energy, bins of energy. And here we basically tell it what we want to extract. So we basically want all that we have. So the counts, so the on data, the background model, the point spread function, energy dispersion and exposure. And then for the in order to avoid regions where we have not so many informations, where basically our instrument response functions suffer from low statistics, we set here a safe mask, which is then kind of like cutting these regions. And we put it here to 2 degrees, which is slightly larger than the magic field of view. May argue for something a bit more restrictive here. But just in order to have only good quality regions. And then we can basically just run over the observation files and can have a look at how these data sets look like. So also here we can check what was produced. Now this is of course only for one data set. Like if you want to check the data sets produced for the other runs, you can iterate over this number here. All right. So this is now just kind of like reading the data. However, now we can undergo the first processing step, and the first processing step is regarding here the background, because actually the background model should already be pretty close to the background level that we have in the data. However, this model here is a little bit simplified, because in order to reach good enough statistics, what was done here during the construction of the background model is that it was one kind of like averaged background model for all the runs, which is maybe not optimal for a single run. So we kind of like first do what we do here is we focus more like on the shape in the reconstruction, and now we are adjusting a little bit the rate of the background in order to have a better fitting background model to each run, in order to match the background rate here. So it should be already quite good, but we can now further fine-tune the shape and adjust it to the actual level that we have in each run. This is done with the so-called field of view background maker. So in GammaPy, there are 2 background makers. One is the so-called field of view background maker. Field of view background maker basically means you are having a model in your observation runs, and you are adjusting the normalization of this shape model. And this is kind of like the field of view background. The other one is the ring background, which is kind of like a method that uses which around each point in your sky map is basically selecting a ring, kind of like an annulus with an inner and outer ring, and counts how many counts you have in this ring, and then uses the background model shape just to rescale account for the area difference in this annulus around each point compared to your pixel. The ring background is usually the more robust method, but it might not be the best method, particularly if you look for an extended source or you have multiple sources in the field of view, then you need to avoid certain source regions. Moreover, it cannot be used for running a 3D spectral analysis. This can only be used for estimating your background level and then to subtract the value. But you cannot run a full 3D analysis as we will do it in the following. For that reason, we are working here with the field of view background maker, which in case you have a well-defined background shape model should actually work just fine. If you want to know more details, then there are some references here about how background models look like, how they are constructed, because that is not kind of like part of it. We assume here, like in case of the future CTA, that your data comes with a background model. So now if we have the shape of the background and we just want to adjust it to your data, you of course want to avoid to include for this fit to include or consider the source regions. You want to exclude them from the fit. You don't want to adjust your background model to those regions because it will cause an upward bias of your fit, because then the fit tries to also consider the higher emission regions where you have sources. For that reason, we are defining exclusion zones around our source. And you need to define an exclusion radius here, which in most cases, something like 0.3, like the larger you can make it, the better it is. However, of course, if you make it too large, then there will be no region left in your sky map where the background can be adjusted. So you want to make it as large as possible and as small as necessary. So then you define your field of view background maker. You give it here the method, in this case fit, and the exclusion mask. So defining the regions that should be excluded from the fit. And then we run over our data sets and we fit the background for model to each of these of the data sets. So for each individual run. You can see here that there is some small if condition included. So this basically shall account for too strong adjustments. So if the fit normalization that needs to be applied to your background model is too strong, then it is actually suggesting that probably your background model is not really, the shape is not really good to start with, or there's maybe something wrong with that particular data run if the fit really needs to scale your background model by that much. Because even though, as I said, it's an average background model here for all the runs, it should actually be close enough to each individual run as well. So if the fit here needs to rescale it by quite a lot, that is something to check in details, and it then gives a warning in that case. All right. Are there any questions up to here before we continue? Okay, then I take this as a no. And now for this analysis, there are like two different methods how you can run the analysis. This is true for the 1D case as well as for a 3D case. You can either run the analysis in the so-called stacked mode or in by keeping the runs separately. So in the stacked mode, it will basically combine, it will collapse all the data sets, and in this and average out the values in each pixel of your data space. Or alternatively, in this case, of course, you have the advantage that the analysis runs much faster because you have only one data set to deal with here with, and it's the quicker analysis, particularly if you run analysis for the first time. What you can also do is you can keep your data sets separately and do a joint fit. In this case, you are keeping the data set separately and you are adjusting your optimal model by a combined likelihood fit across these data sets, which is a little bit, should be a bit more precise, but runs a bit slower. Here, in this case, for simplicity, we actually use the stacked method for the boost in speed and for simplicity. So once the data sets are like stacked, then our stacked data set is ready for our analysis. And we can, for the first time, have a look at the analysis results. So the first thing we can check out are actually simple sky maps. And so this means here the count map, the exposure map, background map, and access, and just look how it looks like. And thanks to some functionalities in GammaPy, we have here this also as an interactive plot. So you can see here that for the you can scroll across the energy range. Now, of course, in the lowest energy range, you don't see anything because we are well above below our threshold. But if we go then in a more favorable energy range, well, maybe that's a little bit too high. We can then start seeing now this is the on map for just to improve the visual impression. It has no real scientific meaning. We have a smoothing radius here. Now this is just for smoothing the maps here and make it visually more appealing. Now this is the on map, so you can already see that here might be some kind of like source, but this is also the center of our observations, so not too meaningful. You can then also have a look at how the background model looks like. Usually just as like centered on the main pointing position, target position. Now for the exposure, we can do the same. Also here, basically looks very similar to the background map. And what is this? I think, yeah, this is already the access map. So here, this is the first one that starts to be kind of like meaningful because it is showing you how much signal you have over your background. And now this is already indicating that there is something in the data, of course. I mean, that's what we expect. There's the source. But you can kind of like already see it here in this very simple maps. And maybe it's a little bit weaker. Maybe let's go one energy bin lower. You can see also the other source appearing here. So that we indeed have here our two sources within this in the sky map. Now, in order to be a bit more quantitatively and to estimate the this detection significance for this source, we can use two different estimators. And how do we interpret the values of the color bar of the last plot? This should be actually, this is the access map. So this is kind of like should be in counts. However, mind here that these counts are smoothed. So you are kind of like smearing out the pixels, so they are a little bit harder to interpret because you're like destroying your Poisson statistic in each pixel. But basically, they are in like smeared counts. Yeah. So for the detection, we have two methods. One is the so-called access map estimator, and one is the so-called TS map estimator. Access map estimator is basically using the counts, very similar to what you have done in a 1D detection case. So you are defining a region around your pixel in which you count your like data counts, and you compare it against what the background rate, what you expect from the background rate, and compute your significance based on this. The TS map estimator works a little bit different. So here, what you do is you are performing a likelihood fit in each pixel, and you assume a test source which you fit in each pixels, and you are estimating the significance for your test source based on the likelihood. So the first one is basically more similar to the 1D case, and the second method is very similar to what to the 3D analysis case, or what you might be used to from the Fermi-Lat analysis. So if you want to compare with Fermi-Lat detection analysis, then the TS map is more recommendable. If you want to compare it to what you have in the 1D case or to counts map, then use the access map estimator. Okay, so let's start with the access map estimator. And you can see here that the first thing we need to do is define a so-called correlation radius. This is basically the size of the extraction region around each pixel. And this should be for about the size of your PSF. Or if you have some extended source, then actually you should consider the extension. You can add, for example, add them in quadrature. That is what you would expect from if your PSF and your source extension are Gaussian shaped, then you can add them in quadrature and put then here the correlation radius. And then you run your access map estimator here and can produce then your maps. So, and since we are working with counts, this is kind of like your Lima significance. And here we just generate or extract the significance map and the number of expected access counts and basically just plot them. And this is what we get. So here on the left hand side, you get your significance. So this is now in terms of sigma of Gaussian. You can see that indeed these two sources are significantly detected. On the right hand side, we then have the excess. And this is kind of like within the, you can also specify here for the access map estimator the energy range if you wanted to have a different energy range than what you selected before for the data sets. Okay. Now, in order to check how reliable here our significance map is, it makes sense to check the distribution of your significance in each pixel. And because you expect that in the regions without a source, so here in the outer part, that you have upward and downward fluctuations in your significance value. And they should follow a Gaussian in the best case. So you should get a Gaussian distribution if you plot your significance per pixel, and it should be centered around 0. And the width of the Gaussian should be 1. So we can check for this. So we take here our map. We include all the pixels which have no defined value, and then we of course want to create the distribution of all pixels, and then we want to create the distribution without the source pixels that we can then compare against the Gaussian. So again, we need to apply here our exclusion region to exclude the regions with sources. And then we basically just bin the data and plot them. And this is what we get. So for only the background bins, so here the bins without the source, we get this purple distribution. And for all the bins, we get the red distribution. You can see that, and just a Gaussian here to guide fitted to the background bin distribution to guide the eye a little bit. As you can see, or it's not perfectly 0, but almost, and it's also slightly wider, but this is usually not concerning if it's not more than, let's say, 10%. And you can see that particularly if you consider all the bins, then the distribution is a little bit wider because it contains our source. So it also contains the very significant bin from the source. Now, where these bins here come from, the very negative ones, I'm not entirely sure, but maybe it comes here from this hole here. I mean, sometimes you have some kind of like artifact. Or if you usually make the maps a little bit wider, then you can also, if you have not very well sampled bins, you can also have some excess here, but it's usually not so worrisome. The main point here of this check is to check that your background distribution here follows a Gaussian. at least approximately. If it does not, if it's very wide, then it's usually suggesting that you have some systematic differences between your counts map and the background map. This can happen if you have an extremely large source that fills almost your entire field of view, or if your background model is not good. Okay. Then for the TS map estimator, things are a little bit different because, as I said, what we do here is we are fitting a test source. So first we need to define our source that we would like to test for. And here we are looking for a point source. You can also put an extended Gaussian or a disk or whatever model you want. For simplicity here, we use a point source. And then you also need to give it a spectral model. And here for simplicity, we use a power law model with an index of 2, just as one of the most basic models. And then we combine this here to a so-called sky model, which we then can fit. Okay. So then for the estimator, we put our sky model. Here we can, as I said, you can, for these estimators, define energy ranges in which it runs. So you're just kind of like a sweet spot energy. And there is an additional kernel that you can apply, like a smoothing kernel. Here I would also recommend to keep it in the order of the PSF. Can also, I think, remove it. The difference here should be minimal. And then we run the estimator for our map in order to get our final significance maps. So now what it does is it iterate for each pixel, it tries to fit a source, and then determines the significance for this additional source based on the likelihood in each pixel. So we are producing here 3 bins. Now the first one is the significance map. This is also kind of like in terms of Gaussian significance. So you can compare this to the excess map estimator, though it's slightly differently constructed. The second one, we now have a flux map. So the excess map estimator doesn't give you any physically meaningful sky map. It's just running with counts. It's just running with statistics. However, here for the likelihood fit, we are considering the exposure, because what we do here is a forward folding. We take our spectral model, we multiply with the exposure, we convolve it with our PSF. We add our background model and fit this to the data. So the exposure information is in there, and we can convert the counts that we have to physically meaningful flux values that we can compare against some theoretical predictions. So this is an advantage here of this method, that it comes basically out for free. And if you talk to a theoretician, he or she will certainly prefer a flux map. It has more meaning than just a significance. No, it really shows you some kind of like intensity. Whereas significance, no, like the significance of a source can be just because you observed one part of the sky longer than another part. You will get a more significant detection in that part than in the other, even though the two sources are equally bright. Whereas the flux map really tells you how bright are the sources compared to each other. Huh? So this is has a quite strong meaning. And the last thing here is the so-called iteration map. So this basically just tells you how many steps the fit needed in each pixel in order to converge. And where the sources are brighter, it needed a little bit less steps to converge. And in the pixels where you basically just get an upper limit or just fluctuations, it takes a little bit longer to converge. Okay, and with this we have detected our 2 sources and can come to the spectral analysis, but I would first like to ask whether there are some questions about this part.
So, Marcel, if I can ask, so basically in the first significance map that we saw, that was basically the Lie formula applied in each pixel, right?
Correct, yes.
While this one, yes, it has this iterative process that you just explained. And
Yeah.
perhaps, Marcel, we can briefly comment on the PSF because I think it's the only IRF we didn't touch upon.
Okay. In which sense? So how the
Just
how
of,
the,
yeah, exactly that. Here we included the other IRF that we included in the data is also the PSF, let's say, because in this case we are not using, let's say, a fixed region to determine the on and off counts, let's say to estimate signal and background. So we don't have the RADMAX table that we had before, but now we need the basically to know how do we reconstruct positions. And this is why we have the PSF now. So if
right.
you
Okay.
if you go back to the presentation that Giacomo did, it's basically now we are integrating also along a spatial dimension when we estimate the counts. I just wanted to say this because yesterday Giacomo prepared an introductory video, and yesterday we also took a look at the forward folding formula, let's say for the 1D case. So you have to imagine now that you are integrated also along the spatial dimension. And for doing that, you need to know how do you reconstruct every photon, let's say, the uncertainty that you have on the spatial dimension.
Yeah. So if you what you can see where you can see the difference directly here is when you go back to the beginning where you have this peak functions over the observations, then you actually here in the point spread function plot C, there are different curves, and you can see that you have here lines for different offsets from your pointing direction. And for each of these offsets, so either the center of your camera or 1 degree offset, you have different so-called containment radii. So basically, how much of your signal you expect in a certain radius around a location at this offset. And usually, you define this in terms of a 2D Gaussian. So one sigma would be 39% containment, which is not shown here. Then you have 68 and 59% containment. So this is kind of like an indication that you have your 3D like you have your full enclosure point spread function model. Yeah. Because then for the 3D analysis, what you want to do is, Cosimo mentioned, you are doing a forward folding fit. So you are having a model which you then need to consider how wide, how much extended this model would be in your data set. So if we go back here to our estimators, then for the access map estimator here, we needed to define a correlation radius. So here, like in the 1D case, you are not really considering your PSF, but you as an analyzer are defining the radius in which you want to calculate your lemma. And this here would then be, for example, a 1 sigma region of a Gaussian. And maybe it would actually be better to make it a little bit larger to consider a little bit more signal. But here you set a cut value. In the other case, the TS map estimator, you don't need to do that. But basically, because the estimator starts with, you basically tell it, okay, how large shall my source be? And then this method is doing a convolution with the PSF and to create a source model that is most realistic or that is best representing your data. So this model is already considering the size of a point source in your data. So that is kind of like the big difference here. So here the PSF actually is already the actual PSF is considered. Because you can see that the PSF at 1 degree offset is actually different than in the center of the field of view. So actually for the correlation radius that we would need to apply for the central source here, that is part of our observations, that where our observations were targeted, is different than the correlation radius that we would need to apply to this source here, which is offset from the center. Now you can also see that probably this here is kind of like elongated. So that's why here the significance for particularly for the source that is not centered is maybe more accurate with the TS map estimator, and for the access map estimator you would need to make the correlation radius a little bit larger. Yeah. Okay. Any further question before we come to the spectral fit? Okay, I hope that kind of like covered what you wanted to mention, Cosimo.
Yes, thanks a lot, Marcel.
Okay, then we go to the spectrum. So similar to the TS map estimator, we are now need to create a model which we fit to our data, and we first kind of like define the spatial model and then the spectral model. Now, for the spatial model, we again take the point source, and we are creating then two sources that are centered on the locations of each of these known sources. And for the spectral model, we basically read the model that you used in the previous analysis, and to have a comparison with the step that you had before with the 1D case. So then you can have a look at the end. You can of course print it, and you get some kind of like summary of what is included in your sky model, where you combine the spatial and the spectral model. Okay, so you have here then the coordinates of the source. You have the index, basically the log parabola and the redshift for both sources. Okay, and the parameters, like for each source, you can now, since they will be subject to a fit, you can of course do things that like you can handle those as fit parameters. So you can freeze the parameters, or you can constrain them. So here's just an example how you can access the parameters of each model, and you can, for example, here freeze the localization, assuming that you perfectly know them from catalogs. Okay. So you kind of like then again, like for the TS map estimator, whatever, you can define here an energy range that is different than the one that was used for the extraction of your data set. If you want to adjust it, for example, now you notice, okay, we were a bit more generous with the energy threshold for the when extracting the data, no, and when they're quite low, but maybe you don't want to include the energy range below your threshold, so we can put it here a little bit higher at 80 GeV, and yeah, and then save this as a mask for the fit, so that it only fits within this energy range. Okay. Now we also create a model for our backgrounds, because we want here to fit the background with our sources together. So the background here, we assume that we don't know the background shape. So, but we say, okay, we have our background model and it has a certain normalization in each of our bins, but we don't actually know what is the spectrum across these energy bins. So this is what we call here a piecewise normalization spectral model. So we basically fit each of the bins here. We fit the background independently. And for we tell that our background field of view maker shall consider this spectral model for the fit. That is something that we have not done before. Before, when we were adjusting the background for each data set, we were actually just applying one scale across all energies. It's just one factor to adjust the background level to each of the observation runs, but we were assuming that the spectrum that is in our background model is actually correct. Here, in order to be more precise, we basically give it as a free parameter. And then our total 3D model consists of the model that we have for each source plus the background model. And this we basically then give back to the stacked data set so that it knows about the models, and we can perform a fit. So here for the fit, you can adjust certain parameters like the tolerance for the fit, certain fitting methods, and the kind of like print level, the number of details that you want. If you want to know details about that, then this is documented in the GammaPy documentation. For simplicity, we use this setting here, and that you basically run the fit for the spectral extraction, and you save then the output of the optimization procedure in this object here, in this result object. The minimizer is used, or this word here, minu is basically the minimizer that is used, the minimization tool. And that's where kind of like this comes from. And then we can have a look at the output. Important here is that you make sure that the results here of the optimization always successfully finished. So if the fit did not converge, then something went wrong and the results are not reliable. So always make sure that your fit results is successful. And the same accounts here for the covariance matrix. So in order to be sure that your uncertainties are also so reliable, not just the mean. Okay, now this is how the tool plots it. It's not really like comprehensible to understand the output, except maybe here for the success, because this tool is already like from construction a little bit older. So the formatting here is more like for a command line, but there's also like a more nicer way to display the final results. And it's that functionality here. So here you have basically all the fitted parameters for the two sources. So for 1ES 1218 and for 1ES 1215. And then you have here a normalization factor for your stacked background. And you have one factor for each energy bin. That's why you have several of these normalization factors. And the ones here is probably here for the highest energy bins. That's why the background really was not fitted there, because we have almost no statistics. So one would need to look here in the medium energy range. Okay. Now this is giving you you can already use this in order to produce a butterfly plot, but we also want to add data points in order to see how they look like. So for this, we can use the flux point estimator similarly to the 1D case, and run this with the same energy edges and for our two sources, and can then compare this later on with the results that we extracted from the 1D case. Now, we can also check here the output of your fit model. So this is always something that we should do, is whether the model that we produce for our two sources is actually describing the data well. And for this, we can have a look here at the spatial residuals across our sky map. So this is basically the leftover counts over our model. And you should not have any significant leftover emission here. Otherwise, there is a source in your field of view that you have not properly accounted for. And as you can see here, it looks quite well. So we don't have any like significant deviations from the from around zero. Kind of like everything is fluctuating here in the range around zero. So that is good. Also, if your source is, of course, overestimated, then you would create negative excesses in these regions. You can see maybe some kind of like a bit stronger deviation here where we have our strong source. This can sometimes happen if a source is very strong. Then you start seeing a deviation between your the real PSF and the PSF that comes is in the Monte Carlo simulations, and then the PSF model is not perfect anymore. But and you have some kind of like leftover residuals where you have your super strong source. However, this should really just happen for the very stronger source, and even there, it should not be too problematic. But sometimes you can see it for crab, which is just in a different league. There you can sometimes see some leftover emission that is not properly accounted for due to differences in the real PSF compared to the Monte Carlo PSF. We can also see the residuals in terms of energy. So here you can select a certain region in this residual map and plot what is the residuals in terms of energy, or how are they distributed. So for this source region here around 1ES 1215, the residuals around for that locations look like this. We can also, of course, use our access map estimator and run it now over the residuals. Check whether there's any leftover emission. And here you can see this issue, this deviation that comes that I mentioned coming from the PSF a little bit more clearly. So you get a little bit like, because this difference in the shape, you are get this nearby significant and negatively significant regions. This you get for very strong sources. You can see that at the higher energies, where usually our PSF is much better, or Monte Carlo PSF and the data agree much better, you don't see that effect. So yeah, it's more visible at towards the energy threshold. Okay, and finally, we can compare our flux points between the 1D and 3D analysis results and plot both of them. And yeah, here we can see that particularly for the brighter source, we have an almost perfect agreement between the 1D and 3D analysis. For the a little bit weaker source, we do see some deviation here. But kind of like this is mainly driven due to the points at the highest energies now, where maybe here particularly this extremely low upper limit. So we would also need to check whether our statistics here in the map is actually good enough. But given the data set here, I think we got quite a nice agreement. Okay. And with that, we would already reach the end of this notebook. I hope so far everything was understandable. Or if there are some questions, I'm happy to take them. Otherwise, I will just want to add that, of course, there's way more in the like methods or tools like available within the GammaPy package, particularly when it comes to 3D analysis. You have seen that maybe there are a lot of tutorials on the GammaPy webpage. And for example, we have not yet covered here the joint likelihood fit that I mentioned when you don't stack the data sets. So there's quite a lot to explore further. However, I hope that this notebook serves as a starting point for you and helps you to kind of like get into the 3D analysis. Well, I mean, for when comparing the 3D or 1D case, well, there are certain things that a 1D case can not handle, in which 3D analysis is always recommendable. This is for sources that are very large compared to your PSF. Or that are in some kind of like very offset from your pointing direction. In that case, 3D analysis is recommended because it can better account for the variation of the instrument response functions at the source location. So another case is if you have overlapping sources, because then, like you don't know to which source an event belongs. But if you fit two sources simultaneously, then you can properly extract the flux level. So in these two cases, 3D analysis is what I would say a must. The 1D analysis case is, of course, the simplicity. It's much faster. It is also kind of like a little bit more robust in case you have low counts. So for very, very short observation, a 1D analysis might be the better choice. Yeah, so they are kind of like, see them as complementary. Um, yeah, there are kind of like some extreme cases where you need to opt for one. These are the ones I mentioned. So the 3D case needs always a little bit more statistics in order to fill the data sets and to fill the IRFs properly. So for very short exposures, you may not get very satisfying results because you have a lot of noise in each pixel.
Okay. If there are no any other questions or curiosity, thanks a lot again, Marcel.
Yeah, I mean, if there are
And
questions later on, then of course, feel free to reach out. Yeah, don't hesitate. And you can contact me if there are further questions later.
thank you, Marcel.
Thank you.
Okay, so we have been connected for 2 hours, so let's take a 15 minutes break and let's say we reconvene at 11:20 with a Pulsar tutorial by Giovanni. Okay, so see you in a while.
So, hello, let me share the screen. Portion of screen. Let's just take what is useful, yeah. So, hello, this is the tutorial on pulsar analysis. To do this, we will use some archival magic Geminga data. Geminga is a middle-aged pulsar that was discovered by Magic in 2020. So if you open the notebook and you have the data, you will see there is here an introduction which covers a bit why pulsars are interesting and what are the differences with the analysis of other similar sources. Essentially, pulsars are periodic sources, very precisely periodic. Yeah. So what we do is to study their emission as a function of their phase, so the angle that they present to the observer in time. This allows us to, for instance, in this image that I've put here, identify a region of the magnetosphere of the pulsar that emits much more than all the rest. Yeah? And this is of physical importance for modeling of these objects and understanding their emission mechanisms. Yeah? So essentially, phase is the angle, but we refer to it as a unitless number. So phase of 1 means 1 full turn of the pulsar. Yeah? The period and the period derivatives of the rotation of the pulsar need to be known a priori. The period varies slowly or maybe not so slowly for young objects. But this variation needs to be accounted for, especially because in Cherenkov astronomy, we collect events very slowly for these objects. We need several hours to be able to make a detection of a pulsar in the best case, which means that the observations are spun across a large period of time. And this large period of time means that we need to take into account the variation of the rotation of the pulsar during that time. Yeah. These rotation models are called pulsar ephemeris. Their creation and how to apply them to the data is beyond the scope of this school. So in the data that you have available and that you can analyze with this Jupyter notebook, there is already a column for pulsar phase inside. Yeah? Magic data also doesn't have a native way of getting a phase through Python. We rely on an older program that is written in C++. This school is focused on gamma pi, so we will cover this another time if you are interested. Yeah. So let's dive in, and you will see that it isn't really complicated at all. It is essentially the analysis of a 1D source, of a extensionless source, because pulsars are extremely tiny. There is another, apparently my browser has decided to crash right now, but we solved this, yeah? There is another case in which you might be interested in pulsar analysis, and that is if you are studying a PWN that the pulsar sits into. At the energies of Cherenkov telescopes, it's very negligible, the contamination of the pulsar signal into the one of the PWN, but it is of importance for Fermi-Lat analysis. So one other case in which you might be interested in pulsar is if you want to remove the pulsar signal to study the, let's say, DC, yeah, continuous emission of the PWN. Yeah. So one typical diagram that we use in pulsar studies is what is generally called the phaseogram. It is also called the phaseogram or light curve, just to confuse people a bit more. This is different than the light curves of the AGNs because it covers the very short time interval of the period of the pulsar, which is less than a second, yeah? Stacking the events across multiple hours of observation. There is no native way of doing a phaseogram in gamma pi, but we can rely on the matplotlib functions for this. The only caveat that we need to apply, that we need to be sure we are applying, is that the events of the pulsar need to be cut with the gamma-ness and also theta square radial cut, yeah, which is similar to what is done in 1D analysis. If we pull the events just out of the FITS file, they will have the gamma-ness cut, because this is what happens when you convert the native magic format into DL3, but the radial cut will be stored in a separate HDU of the FITS file. So here we are simply including the necessary packages, yeah. We are defining an energy range in which we want to plot this phaseogram. This energy range is necessarily in reconstructed energy, yeah. You are close to the end of the school, so by now I'm sure you know very well the difference between reconstructed and true energy. We cannot give true energy to a single event. Statistically, we can give a true energy to an ensemble of events, but here we are selecting events one by one, so we only have access to the reconstructed energy. We will see in a moment where this, what is a meaningful method to get these limits that I've set here. And then here it's really simple. We just load the data. We cycle over the files. We read the events one by one, their energy, their position. We read also the energy cuts from the other table in the FITS file, and then we apply a mask. Here we are cycling over the possible energy beams of the energy-dependent theta square and gamma-ness cut, and we create a mask of the events based on these beams, and then we take the global OR of all the beams. So effectively what we are doing is to keep only events that satisfy at least one condition in the theta square gamma-ness cut. We see that after doing this, there is a certain number of events that survived, and we can plot them as a function of phase. This is just really plotting to obtain the phase diagram. Yeah. So this is a typical phase diagram with phase spanning from 0 to 1. The choice of what is 0, since it is a rotating body, is completely arbitrary. Yeah. In this case, the choice is done in accordance to Fermi-Lat, so that the diagrams can be compared directly between Fermi-Lat and magic. Yeah. And here you see that there seems to be an emission, a pulse in here. Now, this is more a topic for statistics. If we didn't know anything, we would have to rely on some statistical tests to assess how significant the presence of this pulse is. But since we know where the pulse is located in Fermi-Lat, and it is this P2 region shaded in green, we can simply sum up the events that fall inside this green area and calculate the Lie and Ma significance. I stress that it is very important not to adjust the width of this region where we are searching the signal. This is true for the case of pulsars, but for every possible source after seeing the data. If you adjust the definition of the signal after you have seen the data, you are introducing a bias, you are introducing a trial factor, and then to account for it, you would have to simulate at least 10 million of these phasograms, empty, all empty, and look at them one by one to see how often you see an emission similar to this one. Yeah. So here we are calculating this Lima significance based on regions which were predefined. Yeah. The good thing about pulsars is that most often they have an area, a region in phase, so a certain time during which they don't emit any gamma rays. Now you have just emerged from the very nice review of 3D analysis by Marcel. You have certainly seen how important it is to have a reliable background estimate in gamma ray studies. In the case of pulsars, essentially your source turns off every second, yeah? In case of Geminga, the rotation frequency is roughly 4 Hertz. So 4 times per second, Geminga disappears from the sky. This gives us the power to estimate the background from the time intervals where we know that there is no pulsed emission. And this allows us to give a very reliable background estimate because it is simultaneous, at least down to 4 times per second to 4 Hertz with the data. It is in the same position in the camera, so we avoid inhomogeneities in the camera that can produce systematic effects. It is, let's say, possibly the perfect background estimation or close to perfect. We will see that this is important for the case of pulsars. Yeah? So here, if I take this P2 signal region that we had found for Fermilats and this off region here, I'm just counting how many events are inside each of them. And then here, this W stat count statistic is just the Lie and Ma statistics, and we can calculate the significance of the emission. Just as a cross-check, we can also calculate it manually. Yeah, the Lie and Ma 17 formula is not that difficult. It is trivial to implement it. Yeah, we see that obviously they give the same results. And that the emission is indeed significant. It is at the level of 6.4 sigma. So with this, we can already claim that we have detected Geminga from this data. It might be surprising for you that we are using a plot that has events on the y-axis without accounting for any IRF to claim the detection of the source. This is simply because at the time scales of the pulsar phenomena, which is sub-second, the IRFs are constant. So when I stack all the data across many hours, the resulting IRF will be the same for this phase bin at 0.2 and at 0.8. So we can use a plot that hasn't been accounted for the IRF to claim the detection of the source in this specific case. So this was basically on the production of the phase diagram, commonly shown plot in pulsar studies. Now we are going to go into the spectra. You will see it's a fairly simple 1D analysis. Before this, I'm asking if you have any questions or doubts or anything else, or you want to throw tomatoes at me.
Just a comment, Giovanni. Actually, in the first notebook, when we did estimate just the significance of the crop, in principle, we didn't use the IRF either. So we just took the on and the off counts, and we didn't use any knowledge from any value, any data from the IRF.
Sure. I mean, it can be meaningful, yeah. An important difference is that as I was mentioning, there is this background issue, yeah. So most typically when you do it for a I will call it DC, non-pulsed source, you get a significance value from the on-off and excess strategy. But you also have to make sure that the signal-to-noise ratio is at least a good fraction of the background, because background fluctuations, which are not accounted for by the Lima formula, because the Lima formula gives a statistical significance, doesn't know anything about the systematics. It could create a fake signal very easily. I remember this was 6 years ago at a magic meeting. There was a nice presentation where it was shown to people that you can easily create a Six Sigma signal from off data if you just adjust the cuts a bit and are not careful about what you're doing. In this case, since the background is more reliable, you can relax this condition on the cutting at the certain signal-to-noise ratio. I see that probably Cyrus is telling me that there are no fresh tomatoes in Germany. Sad. We should go to the Netherlands there. And Julian has the hand raised.
Yeah, Giovanni, I was wondering, are there any pulsars that are so bright in optical that they could produce a problem with the phasogram background? Because in principle, if you have very intense optical emission, that would produce problems with the background also at the timescales of the pulsar machine.
This is very, very good question, Julian. No, fortunately or unfortunately, depending if you ask us or the optical astronomers, there are no bright optical pulsars. I believe the brightest is the Crab itself, the Crab pulsar, which is of visual magnitude of 15. So for us, it doesn't pose a threat. Yeah. But you're right. If there were extremely bright pulsars, the background would be affected by the optical emission. In this particular case, the Geminga optical pulsation, it exists. It has also been measured once. It is of magnitude 27, so it is dimmer than the night sky background. Okay, if there are no more questions, we can go on with the spectra. And this is really, from the execution point of view, it is really very simple. Everything that we need to do is to include this class here, the phase background maker. And the rest is really, really similar to what you have already seen with the 1D analysis. We load the position of Geminga, we define our target, we define our energy access. These here have weird numbers because I took them to be the same as the ones that were produced by Mars. Also, these files were processed with some tailored Monte Carlos that track the position of the pulsar in the sky and that have more events towards the lower energies than usual. Because we will see in a moment that this is relevant. This is stuff that you've already seen before. We are loading the data. Here we just calculate the effective time of observation. It turns out to be something like 80 hours. We can also use the statistics that we had before, that we had calculated before, the 6.4 sigma, to calculate a figure of merit in the extremely unsettling nightmare units of sigma over square root of hour, or the square reverse, which is just hours, and it is possibly giving less nightmares. Yeah. So we see here that it takes 2 hours to accumulate 1 unit of TS. It's roughly variance. If we wanted to have 10 sigma, it means a variance of 100. Yeah? It means that we would have to observe the pulsar for 200 hours. Yeah? So here, this is really the place where we are setting up the objects for the analysis. We just define the geometry. Then we use this information that we had from Fermi-Lat of the on and off phase. This on phase is just the same as the green area of before in the phase diagram. And the off is where we will take the counts to estimate the background. And here, this is just how it works. You create a phase background maker object, giving these intervals and the name of the pulse phase, of the column in the fits file that contains the phase. These files use this name pulse phase as the name of the column because it is the same name that is used in Fermi-Lat. So it is for consistencies, I use the same name. In principle, you can name it everything you like. Yeah. And really then it just becomes a matter of 1D analysis. So we load here the data set. GammaPy produces a nice enormous string of warnings. And we can have a look into the IRFs just to have an idea of what we are dealing with. Yeah. You see that the counts and over the background are really tiny. This is what I was mentioning before. The signal of these pulsars is generally very, very dim and at very low energies. Yeah? We have here an estimate of the exposure. And what perhaps is a bit different from what you've seen before is the energy dispersion. So this matrix of energy dispersion is singular. You see that going to lower and lower energies, below 20 GeV, even in true energy, more and more energies get attributed to the same reconstructed energy. Yeah? So here I just pulled out this plot and made it a bit larger. It is rotated because so was the convention in Mars once to have the reconstructed energy on the x-axis. Doesn't matter. I mean, you can plot it the way you want. Yeah. Essentially, this matrix tells us that we do see true energy events that are between 10 and 20 GeV. Yeah. But the reconstructed energy that is being given to these is above 30 GeV. This might be surprising, but it is actually the very reason for which we are able to see these extremely low energy events. Essentially, they interact by chance in the atmosphere. They have a lower first interaction point than usual, and therefore more light reaches the telescopes. This allows us to detect them, but at the same time, it makes them look like if they had higher energy. Yeah? So this is a territory in which the usual methods that we employ become shaky because we have very large resolution, very large bias, even up to 100%. So we have events of 15 GeV that our analysis says they are 30 GeV, twice their energy. This is bias 100. So indeed, this poses some difficulties for the analysis, and it is the reason behind this usage of extended Monte Carlos with higher statistics at the lowest energy. Yeah? A plot which I like to produce is the same, so this migration matrix, but multiplying, normalizing it to the spectrum of the source. So we multiply every row of this column by the unassumed spectrum for the source, and we obtain something that looks more or less like this. So this is a section of the migration matrix weighted with the spectrum of the source. It shows us where these events really are in energy. So here we see most of them are above 20 GeV, but not beyond 40 GeV. And where our analysis tells us they are, it says they are above 35 GeV in reconstructed energy. This plot, for instance, can be used to determine those limits for the phaseogram a priori. It follows the phaseogram in the notebook, but it should be used before producing the phaseogram to determine these energy ranges where we expect the pulsar signal to be present. From a very similar procedure, we can also plot the analysis threshold, so the peak of the distribution of the Monte Carlos, which for this analysis turns out to be around 20 GeV. So we are really at the lowest end of the EACT technique. You can go a bit lower with larger and better telescopes. Recently, the LST-1 telescope obtained exactly on Geminga a threshold around 10, 13 GeV. But below 10 GeV, you stop seeing the ellipses of the events. So the technique breaks down essentially. We are pushing it to the extreme here, to the extreme low energy. Of course, we can also have a look at the exposure. These data were taken with a special trigger that helps increasing the exposure at the lowest energies. It is a trigger similar to the one that is employed in LST. Okay, let's have a look at those very little counts we had before. We can do some statistics here. And calculate the total excess counts. It's around 2,500 counts over a background which is 150,000. So we have a signal to noise ratio which oscillates between 1 and 2%. As I said before, this would be a problem in a regular analysis because you would have to make sure that your background doesn't fluctuate as much as producing just by chance a 1% signal. In case of pulsars, this is kind of ensured by the fact that we are taking the background during the time in which the pulsar is switching off. If we go and have a look to the histogram of the events, of the on and off events, it's practically impossible to see the on events because it's only 1% of the background. If we zoom in, we kind of see that there is some signal here. And as expected, there is nothing below 25 GeV or above 100 GeV in reconstructed energy. If we can also plot directly the excess events, and then we see the accumulation here around 40 to 50 GeV. From now on, it is really just a normal 1D analysis. So we can fit a power law. I'm sure you have seen this already in the school. These initial values are taken from the previous magic paper on Geminga. So we can just fit it and we obtain the values of the power law index, which is around 5.2. It is extremely steep. You know that for an SED, an index of 2, here it is positive defined, so an index of 2 is flat. Here we are three whole powers, decreasing. So it decreases very fast. It is a very soft spectrum. And we can have a look at the results of the fit and the covariance between the parameters. The reference energy is obviously fixed, so it has no entry. There is a large covariance, negative covariance between the pivot value and the index. This is kind of normal and expected, because if you raise the power law, the fitter will try to make it steeper to fit the data better, and vice versa. So most typically what we did, well, here we have a comparison between what we get out of this data and the results that were published using Mars before, the standard magic analysis software. You can see that they match well within the statistical uncertainties. And then the rest of the notebook is just a iteration of this concept. We can also use the joined fit instead of the stacked one, and we obtain something similar. We can also fit a log parabola and then go and check the significance of the curvature. In this case, you see the green here is the log parabola, and the significance of it, if we go and check this beta value, which is the curvature parameter of the log parabola, is very low. So these are likelihood fits. Gamma pi, everything is a likelihood fit. A fit with a log parabola will always be better than a fit with a power law, because a log parabola includes all possible power laws as a nested case. This allows us, for instance, to use this likelihood ratio test, which we can, because the hypotheses of Wilks' theorem are satisfied, to test how better the log parabola is compared to the power law. We will never be able to test how better the power law is with respect to the log parabola, because the log parabola contains all possible power laws. In this case, what we get out of this analysis is that the log parabola model is not sensibly better than the power law one, which hints that maybe the spectrum continues as a power law. Investigations on this topic for these pulsars are still ongoing, also with LST. And similarly, we can do the same also with the joined method. Now, there is this disclaimer at the end of the notebook. I hope you don't take it as a rant. I mentioned before that because of the migration matrix being singular at the lowest energies, this creates some issues. One issue it creates is with the spectral point estimator of gamma pi. It can be run on the data and it produces spectral points which are valid, but which are very weird in the sense that their size changes continuously. And this is a limitation of the algorithm, not of the implementation of the algorithm, of the rational bit of it, really, with these very high bias and resolutions. So for these very soft sources with a very high bias. Different collaborations have different strategies with this respect. Hess doesn't publish pulsar spectral points. So we remove the problem by just saying this algorithm doesn't work well for these sources, so we don't show the points. It's a very agnostic and honest strategy. Yeah, for LST, spectral points were published, but there was a disclaimer in the paper saying that there was this issue. We have never published a pulsar spectra analyzed with gamma pi in MAGIC. There is an experimental way to essentially implement an alternative spectral point estimator. If any of you is interested in this, I ask you to contact me and maybe we can work on this a bit, yeah, to keep this work going. With this, the notebook is finished. If you have more questions, please ask. And yeah, I think we still have 15 minutes, so we have time for some questions. Thank you.
Thanks a lot, Giovanni. If I can, I would like to to ask you if you could go back explaining the concept of how you transform the migration matrix with the spectrum, because the spectrum is in true energy, but you are multiplying the reconstructed energy distribution, right? You're multiplying along the rows, right?
Basically, this here, which is the standard migration matrix, it is normalized in such a way, let me think, that each column, that each row sums up to 1. Yeah.
In this case, yes.
Yes. So what I am doing, row, because I twisted it, otherwise it would be column. Yeah. Essentially, I am weighting each row, in this case, based on the spectrum of the source.
Okay, see, so you are reweighting the PDF of each energy estimator, let's say, for its true energy. Okay, got it.
Alternatively, you could make this plot by weighting the events one by one. This can also be done. It could marginally be different. I like this type of plots because, yeah, it gives you a snapshot of where the events are in reconstructed energy and where they are in true energy, basically. So what you are saying, what the energy estimator is saying versus where it is.
Yeah, where it is.
For a particular source. If you integrate, if you project this.
Then a general question that I have, I don't know if someone else has had trouble with importing Landau from SciPy stats.
Oh, really?
Yeah, when I was trying to do it, it tells me that cannot find Landau.
I suppose maybe they changed its position. Yeah, so I can have a look at the version here. Can do it here, no?
Did anyone else have this issue? I think I remember Sarah reported it, but I forgot to
Yes,
fix it.
I think someone in the GitHub repository said it would work if you update your SciPy.
Okay.
Yeah, Elia mentioned it. So
I didn't import it. Yeah.
Okay.
Fine. Sorry.
So I think, yeah.
Yeah, so this was version 1.16.0.
Okay.
I think they changed the position of where these functions are. So sorry if this is not working for some people.
Yeah, I have 1.14. Okay, thanks. Any other question or curiosity? I think something really interesting that Giovanni is showing that we didn't look at yesterday is the covariance matrix of the parameters. In this case, maybe we didn't take a look at it yesterday. In this case, maybe it's not so informative because you have only two parameters, but you can still see how they are correlated. But when you have many more parameters, it's really interesting because it tells you, let's say, how one change in one is correlated to, let's say, a change in the other. And I think it's really interesting when you have models with more than, let's say, two parameters where you have potentially degeneracy, where you cannot distinguish a total change in the function, which with let's say, change in different parameters might produce similar changes in the total outcome of the value of the function.
Yeah.
So exactly, for example,
you should, in general, it would be a good way, a good thing to keep away from correlation one, yeah, as much as possible, apart on the diagonal, because obviously the parameter is always correlated with itself, yeah. In the worst cases, it could mean that your model has two or more parameters that affect the same thing, yeah. And then it is impossible to distinguish between them. Also, if this is the case, the usual theorems like this Wilks theorem of the likelihood ratio, they are not really applicable because you have multiple degrees of freedom that do the same thing. Yeah, it's like trying to fit a straight line to some points with three parameters. There are only two parameters, so those are the ones that you should fit. Yeah.
Okay, thank you, Giovanni. If there are no
questions, thank you for your attention. I hope it was at least partially informative. And have a nice day and have a nice rest of the school.
Thanks, Giovanni. Okay, we can switch now to the last tutorial if Fabio is ready.
Hello, can you hear me?
Yes, hello, Fabio.
Hello everyone. So now we are switching to a topic in which we want to mix different observatories and different kinds of data sets. So I'm going to start with some slides to show you what we're talking about and how we're going to proceed. And then we're going to move to the notebook that was on GitHub recently. So I hope that you have updated and got the latest notebook that is name number 7. First, I'm going to try to share the screen. So I'm going to try to open the chat. Okay. So are you seeing some slides or no?
Yes.
Okay, the one that says Fermilat with gamma pi?
Yes.
Okay, great. So this is just to explain you how we're going to proceed. And so as you have seen in the previous tutorials, the idea is that with gamma pi, you can load Cherenkov data from different instruments, HAS, MAGIC, Veritas, and CTS simulation for now, and ASTRI. People have done it with ASTRI also. And in those cases, you always start from what we call DL3 event. So DL3, as you've seen, is the list of the observation where you get gamma ray-like events. And the first step that you have done in the tutorials was to use the makers to go from a list of individual events. And then with a field of view background maker, rig background maker, etc., you go from a list to a bin dataset. So the bin dataset will be what we call DL4, in which then you have a 1D, 2D, or 3D event that are binned into image cubes or a spectrum dataset, for example. And then you can proceed in doing the spectra, the light curve, the pulsar analysis, the skype map, etc. What we're going to do with Fermi is that we're not going to do the DL3 step in GammaPy because GammaPy doesn't know how to produce the PSF of Fermi, doesn't know how to produce the exposure map or things like that of Fermi. And this will be done externally with the official tool that is the Fermi Science tool and its Python wrapper that is called FermiPy. So I have pre-generated those steps for you, and they are on the GitHub. And the idea is that with Fermi, you start from DL4. So you start already with a data set, and we will read those data sets and proceed forward from DL4 to DL5 and DL6. But what is important is that for now, and it will be maybe complicated to do so, the Fermi spacecraft information, for example, in order to produce the exposure map, you need to know where the spacecraft is pointing and it's rotating in the sky. And so you need to read the coordinate of the spacecraft and produce an exposure map. Clearly, this is not what GammaPy was designed for, and it's already done with other tools, so we don't bother with that, and we start from DL4. And once you have that, what is interesting is that, yeah, you can do multi-instrument. And this is something that GammaPy can do, is that you start from multiple instruments. It could be Fermi, in this case, it could be Hess. You could also do a joint fit with Hess and Magic, for example, where you want to do they don't cover exactly the same energy range, maybe, and with CTA and Fermi, for example, or Hawk, for example, as well. And the idea is that each instrument will have the things that are on the right side of the screen, where if you can produce DL4 for each of those instruments, this is to say a counts map, the exposure map, the PSF, some kind of background map, and also the energy dispersion. So basically it's the observation plus the IRF. Then given a spectral model that will be the same for all of those, you can use the spectral model, convolve it with the PSF, the exposure, the background, and the energy dispersion, produce the predicted cube, so the n-pred, and compare it with the counts map individually, and this will give you a likelihood. So the idea is that you will have a Fermi likelihood given the model, a CTA likelihood, a Hess likelihood, etc. And then you can just sum those likelihood and minimize the parameters of the spectral model and to try to get the best fit using jointly all those information. And the nice thing here is that each instrument will have its proper background handled, the PSF, the energy dispersion, etc. And so you do a forward folding for all of those, and then you sum just the values of the likelihood. And so this is something that so far has not been done a lot, and this is not the standard way of doing. For example, if you do a multi-wavelength analysis, like in this case, this is a blazar, you can have observation from X-rays, you can have information from Fermi, and then you can combine it with Cherenkov telescope. And the traditional way of doing is that you compute flux points, so the points that are shown here with error bars, and then with whatever software you fit a power law, broken power law, or in the case where you fit a physical model, you can do that with NIMA, for example, where you fit inverse Compton, things like that. The problem is that you will do that with a chi-square, so each point has an error bar, and you will do that with chi-square. This is what NIMA is doing, for example. But however, this is not statistically correct because of the energy dispersion, the points that you are seeing here might be correlated depending how big is your energy dispersion matrix. Also, if you have an upper limit, it's really hard to compute a chi-square when you have an upper limit. There is no very good mathematical way of doing it, because what you really need is the profile of the likelihood, which usually we represent with 1 point, but the correct statistical information is the profile likelihood for each of those points, which is usually never computed or given in those plots. And so if you have only detections, it's bad. Maybe it's not so bad, but if you have upper limits, then it becomes statistically completely unreliable. And the other thing is that if you use X-ray points, then producing flux points in X-ray is not a trivial thing to do, especially because the sources can be absorbed, and how to deabsorb the source with taking into account the correlation of the error of this absorption is never done in a proper way. So if you want to fit a model to this, then the best thing to do is to do the multi-wavelength forward folding, what I introduced just before. And this was done in that example for this AGN, where it was done even down to optical and to X-rays, and combining it with Fermi-lat, where a proper forward folding was done for all those data sets. They were all loaded in gamma pi, and then a physical model was fitted into this. And then you can handle really properly the absorption, the EBL, etc. And so, and also then you can fit, if you have NIMA in gamma pi, you can fit the synchrotron inverse Compton component properly. And so what you get out of it is that, no? So yeah, so this was the idea, is that with gamma pi here, with one tool, you can use one tool to get all of those wavelengths. So far it's been tested from UV to KV, GeV, and TeV in that article. There are some work ongoing to also add a neutrino that you could, if you have a flare of a blazar and you have some neutrino information, you could also do a forward folding with an instrument and compare with the neutrino one. And the other small slide that I wanted to show you was this one. Do you still see the new slide now?
We do.
Yeah. And so this is a comparison. This is a corner plot that was obtained in that same paper with the flare of OP313. If you do a fit on the flux point, which is shown in blue, and if you do the proper way, that is the joint likelihood starting from DL4 data and forward folding all the instruments in orange. And so you can see that the results are not so different, but they are not the same. And in some cases, for example, for some of the parameters, you can see that there is a bias, and that clearly, probably, here we don't know the ground truth, so we don't know which one is right, but we know that statistically, one is not the proper way to do it, the blue one. And so probably the orange one is the more correct one. And you can see, for example, for the normalization, the amplitude of the high energy component, you can see the distribution of both, and so they are not the same. So that's one example. And in order to do that, we need to be sure that gamma pi, which was not designed to do X-ray analysis, is compatible with the traditional tools. And so, for example, in that paper again about OP313, this is what was done. And so this is a comparison where you take the same data and you fit it with Fermi pi on the left. In the middle and in the right panel, those are X-ray data, and they were fitted in XPEC, which is what people use. And in black, this is the error on the index and amplitude for some power law model. And in red, this is the same thing done in XPEC or in Fermi science tools. Forget about the blue in the middle. But so what you need to look at is red versus black. And you can see that gamma pi and XPEC or Fermi pi give exactly the same result within the error. Gamma pi in some cases is a little bit shifted, but I mean, this is completely within compatible. And so this was an interesting check to do, is that we can trust that gamma pi can do X-ray fitting, and we can trust that for Fermi analysis, you will get the same result as you were doing the Fermi pi analysis. So once you do that check, then you can do those kinds of analysis and really do forward folding for across the different energies. And here are some examples of what people have been doing. So in the central panel, you see that example for that AGN. On the right-hand side, this was for a Hess source with an XMM upper limit constraint in which if you do an inverse Compton model, then you can derive some constraint on the magnetic field because you don't see any X-rays. And also people have been doing some X-ray analysis. For example, on the left panel, you see that is a P-WIN, the so-called Hand of God nebula, MSH 1552, where Katharina Egg has been working on loading and working with X-ray Erosita data using gamma pi and then combining those data sets from combining Erosita, Fermi, and Hess so that you can look at the P-WIN across the board. And so what is nice is that then you can model, for example, the energy evolution of the P-WIN, which has not the same size in X-rays, in Fermi, and then in Hess, for example. All of that within directly gamma pi. So that was for the introduction. Any question on this before moving on to the tutorial?
Yeah, just a curiosity, Fabio. Might the bias, the shift in the estimation of parameters, might it be due to the fact that you are actually not considering the upper limits?
Yes. You can see that in that case, there were very few upper limits. So I don't think this is the driving point here. The Fermi data points were not super, have larger error bars. I think it can come from many different things. Is that, as I said, for example, in X-rays, the source is absorbed, and usually producing the flux point, you will fix the absorption. You will assume that it's completely fixed and there is no error. So the error will not be the same. When you do the forward folding, you fit all the parameters at once. And so the absorption is a free parameter.
Yeah.
And so you will have larger errors on that part. I don't think that people usually, when they do X-ray flux point, they don't propagate the error on the NH. They take the fixed value and that's it. So this will have smaller error bars. And I think that example that is shown here is probably a good case scenario. If you have non-detection in Fermi or non-detection in Hess or non-detection in X-rays, this might be very different. Because if you have a non-detection, as it is the case in here, then this non-detection, you can change the spectral index or you can change also the DNH, and this will give very different upper limits, for example. And here you can play with that parameter. So yeah, so I think this can be, we haven't tested a case where it was really bad, where I expect that blue and orange will be even more separated. But certainly we can come, there are many cases where you have only upper limits in Fermi, and it will be interesting to see. Because again, in Fermi, for example, the upper limit given the galactic diffuse normalization will change, and so this will probably also have an impact on the upper limits. Okay, any other questions or? If not, let's move here. So do you see the notebook now?
Yes.
Yeah, okay. So in this notebook here, we're going to look at some data. So I told you that we can go from X-rays to Fermi to TeV. So far, the X-ray is the most experimental part. And in that notebook, I only restricted here the analysis to Fermi and magic. So you can see some examples here on how to do it with X-rays. So far for X-rays, we only tested the 1D analysis because making a 3D analysis with strand ray is more complicated by the fact that none of the source, except if you have an AGN, are point or disk or Gaussian, everything in Chandra, the extended sources, for example, the p-winds and the supernova remnants, they have some complicated shape, and so it's more complicated to do a 3D analysis because you don't have a good spatial model. So we're going to focus here on Fermi and Magic and Crab. And I wanted to highlight also the fact that in order to make it shorter, I do not fully take into account the energy dispersion with Fermi in that notebook. So this might have an impact on the SEDs, etc. So don't take the SED from the Crab here, from Fermi. It's a quick analysis and some things are not perfect. And so it's not a science-ready SED that we're going to show here. And if you want to read more about the details on how to do that, there is in 2.0 this tutorial that has been updated. And also that's why you had to update to 2.0 this morning. 2.0 was released a week or 10 days ago. And 2.0 brings a lot of improvement to handle Fermilab data. Some of them are performance related, but one of them is the ease of loading the data. So we will see that here. So we'll start with the importation here. And so here, this is what makes your life easier now if you want to work with Fermi data, is that, so for those who have done some Fermi analysis, you probably used FermiPy. FermiPy is a Python wrapper around the C code and the F tools, Fermi science tools. And in order to start your analysis, you need a YAML file. So maybe I can show for those who are not familiar with. Yeah, so this is the file, the YAML file. So it's just defining some parameter for the analysis. So it's defining where your data are. It's defining where you want to output, and then it's defining the morphology, like where is the center of your region, the number of bins, etc. So what GammaPay is going to be using is that it's going to be reading this, where you have your data, and then it's going to be reading this kind of information to construct the map dataset. So it's going to do a 3D cube based on those information and the fits files that it will find in this directory. So what will be loaded is this. So let me show you here. So this is what is inside the directory, Fermi Crab analysis. So FermiPy has pre-generated the binned exposure map. So this is a cube that has the exposure in centimeters square per second in each voxel of the cube. This is the number of counts in the cube. This is the energy dispersion matrix. This is, as you know, Fermi, the brightest emission is from the cosmic rays interacting with the galactic plane. And so this is the model that will be used to model that background. This is the isotropic background. So it's a 1D file, it's a spectrum from the unresolved sources and some Earth limb contamination. And this is the PSF cube. So basically, this is all you need from FermiPy that and this Fermi dataset reader will read this file to know where to find those files, and that's it. And so if you do that, then you can see here that now from the Fermi data file, we have a GammaPy object that is the cube, the dataset here that has this size, and this is a cube with 13 bins in energy. And so, for example, you can do that in GammaPy. And so here we are looking at the crab. So you can see that without surprise, the crab is very bright. And you can see here as you go with energy. And what's interesting is that if you go all the way here, this is the crab between 1 TeV and 2 TeV. So Fermi detects the crab above 1 TeV. So Fermi was never meant to be a TeV instrument. And the effective area between 1 TeV and 2 EV was never really calibrated. So this area for the IRF is not robust, but at least here for fun, we can see that all the way to TeV, you have lots of photons that are detected here. So then I wanted to show you here again, this is the galactic diffuse emission. So the Fermi collaboration has produced a model of the galaxy with the cosmic rays, the gas, etc. And this is the expected emissivity in the region here. So you can see that the PSF should get a little bit better with energy. So the details are a little bit, no, this is the model. So the PSF is not integrated. So no, it's the same. So that's why I was moving and it was always the same. So that's the model of the galaxy. And then this is the PSF. So the PSF of Fermi moves a lot with energy. So here we start at 5 GeV. So it's already rather good. If you start at 100 MeV, the PSF is almost 10 degrees, 5 degrees or something like that. So it goes from 5 degrees to 0.05 degrees. So there is a factor of 100 between the low energy and the high energy. So it's like the Cherenkov telescope, but even worse. So you need to do a 3D analysis, otherwise you cannot handle the PSF variation. So this is the PSF, the 68 and 95% confinement radius. And you can see that Fermi is rather good, really. At 100 GeV, you get Cherenkov like PSF, you get 0.1 degree, and you can get even, you can go below 0.1 degree at a few hundred GeV. So Fermi is rather good in PSF, and probably at 50 GeV, it's probably even better than CTA at some point, depending on the number of telescopes, but you can get below 0.1 degree at 100 GeV, which I think the LST telescope cannot reach, well below 0.1 degree. So then one thing that is specific to, as I said, to Fermi is that you need to handle the galactic diffuse emission. In Cherenkov telescopes, in some cases you have to handle it, but in most cases it's not the dominant source. So here what we do is that this is the file that I showed you earlier, and it's a template model. And so we're going to build a model and we are going to read it with the temporal spatial model, because we're not going to change its shape. We are only going to change normalization and a little bit of the spectral slope. Then we're going to do a 3D analysis. So we're going to define a spectral model and a spatial model like you've done it before. This is the model for the crab. And then you build the complete model for the crab. Here will be the galactic emission, the isotropic emission, and the crab. I should say that in theory, we should have some other sources here that for simplicity I didn't add, and the crab is so bright that if I forget one source that has a TS of 20, 30, 50, it will not make a difference. And this is also because also we're starting above 10 GeV, and most of the Fermi sources are dying, so you can forget about them. But in theory here, you could have some other Fermi sources. And if you go to low energy, the PSF is big, so you need to make a big region of interest. And here it could be up to 50 sources. And so for now, I think this is a limitation in Gamma Pi, is that if you need to load 50 sources, it's not going to be easy to fit, and especially the way the model are presented, and this is printed. If you have 50 sources, it probably can work, but it will not be easy to navigate. So here we took the simple case, the crab, a small region, and we start at high energy, so life is easier for that notebook. So we can define also that I told you that above 1 TeV, the IRF of Fermi is unreliable. So we're going to restrict ourselves here. And below 30 GeV, you know that the Crab nebula, in Fermi, we see both the Crab pulsar and the nebula. And the Crab pulsar is dominating below 10 GeV or something. And so here, as we want to make things simple, we're going to restrict to the nebula part, to the rising part, the inverse Compton part. So we start at high energy, and we make a mask. And so here, there were very little free parameters here. Well, what we wanted here was mostly the flux points here. Okay, so now we have more parameters. So those are the parameters from the model. Why is it negative here? I think I messed with my notebook playing around and so and all above. What do you get in your notebook for the best fit? Do you get something that makes sense? Okay, 1.01 makes sense. 1.01. Okay, so I don't know. I've played around with the notebook and restarting it, I get the same value as you. So the first is the galactic interstellar diffuse model, and it's been normalized to fit the data, so it should be okay. Everyone gets the same thing. That's good. So everyone, it should go close to 1. If you have a value that is very far from 1, then something is not working as expected, unless if you are working on an AGN, you are very far away from the galactic diffuse emission, and therefore you have no signal in your region of interest, and the model is completely unconstrained. So it can go to 0, it can go to 2 or 3. But if you are in a region where there is no diffuse, it's hard to fit the diffuse. So if you're working on an AGN, extragalactic sources, I would recommend to fix the galactic diffuse to 1. And in my case, you have seen that I froze the isotropic because this is the unresolved sources to 1, because in the galactic plane, you are dominated by the galactic plane, and so it's hard to constrain the isotropic. So that's why it's not here. So now the flux points. So you can see that I removed the options and I said n jobs 4 in order to speed things up. And you can see that it should get very fast here, couple of tens of seconds. And so this first part was the part about loading the Fermi. And so you can see here, so it took like 10 or 15 seconds. So I compared this with the Fermi pi analysis, doing the exact same thing, and we were getting almost exactly the same result. So this was a comparison to show that we get Fermi pi and gamma pi to agree on that region. So of course it's a simple region, the crab, super bright, no background, etc. So now we have loaded 2 things. So we have the dataset from Fermi, so the 3D dataset, and we have the flux points that we're going to keep in memory. And now we're going to reload the data sets that were generated yesterday. And this was the stack data set that you saved to disk. So maybe depending on how you do it, maybe this path is different on your, depending on where you save them. And the nice thing also about gamma pi and about this.
Yeah, sorry to interrupt you, Fabio.
Yeah.
I just wanted to comment that I changed the path in the new notebook because I made it similar to yesterday. Someone asked to update the solution to the notebook number 2. And so the path is slightly different, but it should be really easy for you to find it. It should be there because we saved it yesterday, let's say. But the path that you have now is to be consistent with the one in the notebook.
Anyway, if you do this,
yeah, exactly.
If you are here, and you do tab, it's going to show you everything that you have. So you can find it this way. So you should update the path. And yeah, one thing that I wanted to comment is that, for example, in that work with Mireia Nievas on this OP313, one thing that is very convenient also to do multi-wavelength analysis is that if you are working with a group of persons, one person might be expert on NewStar, another one on Swift, etc. And on your computer, you might not have the NewStar science tools, the Swift or the XMM or Chandra. They all are different science tools. Then they all produce OGIP compliant file that you can load in XSpec. But one nice thing to do is that if you load all those data into GammaPy, you save them as data sets. And then all you have to do when people have produced those datasets is that you do dataset read magic, dataset.read XMM, dataset.read Fermi, etc. And so once every instrument produce the dataset and in GammaPy you transform them to a GammaPy dataset format, then all the analysis that you will do after, you don't need any of the X-rays or the Fermi, etc. tools. You can be in an environment where you have only GammaPy that will work. And that's something that is convenient also because maybe you have experienced that in Conda, sometimes if in the same Conda environment you want to install Fermi, GammaPy, XPEC, etc., in the same Conda environment, sometimes you can have some conflicts. So that's one thing that is nice here is that you can produce them separately and then read everything directly in a dataset. So this is the dataset that we had yesterday. Here, yesterday, we tried, for example, some different spectral model. Here, a log parabola spectral model, and that this is what was obtained. So previously, we had generated some flux points from Fermi, and that we're going to show here and to display them here. So in dark red, this is the magic that was generated previously. Then we have the dashed line is the fit from that paper, and then the green one that you see here are the one that were produced a few cells above from Fermi, and that goes from 30 GeV to 1 TeV. And so you can see that they are in rather good agreement with magic. One point is a little bit above at 100 GeV. I don't know exactly why. Again, it might be that we didn't handle all the extra sources in the region of interest, so we might have an excess from something else. An excess at 100 GeV is a bit strange, but again, this was a quick and dirty analysis. I didn't fully model properly the entire Fermi region around the crab. And you can see at low energy that the first data point is slightly going up, and this is because at 10 GeV are dominated by the pulsar, and so you are still seeing the tail of the pulsar. So if we did the Fermi analysis from 100 MeV to 1 TeV, you really see the two bumps that it is coming from the pulsar emission, the pulse emission in Fermi, and the nebula. So, but otherwise you can see that 200, 300 GeV and above, Fermi and magic are in really good agreement in this region. So we can do different things. So we can test as it is loaded and it's easy here. We're going to do a test where we will do the good way, which is the forward folding with Fermi and magic. So we're going here to redefine the model here. So previously we tried the power law, and here we're going to do the log parabola model. And so one thing that might not be very obvious, and that when doing it, I had to be sure, is that how do you tell that the crab model is the same for Fermi dataset and magic dataset? And so, because in Fermi, you have the galactic diffuse model, which you don't have in magic. And the background in magic is not the same as the background in Fermi. And so you need two different models, but one thing is in common is the crab. So here what you do is that dataset Fermi has the diffuse interstellar medium, the isotropic, and the model from the crab. The model from the crab is not, could be different in spatial shape, for example, if the extension was different. But here, the log parameter model here is the one that was defined earlier here. So this object here is not a copy, it's the same. So if you use the same spectral model in two different models for two different datasets, it will be a pointer in memory, and so the fit will be joined for this one. So this is not obvious And so you need to be careful that if you recreate a log parameter model here, those will be two different, and you will have one log parabola for Fermi and one log parabola for magic, and that's not what you want. So you want one spectral model that covers both instruments, and this is the way to do it. One way of looking and being sure that it works is that, for example, if you look at dataset Fermi models, you can see that you have the diffuse emission, the isotropic, and you have the crab. And in dataset magic model here, you will have, so let's, yeah, you can see here that you have the log parameter model. The name is different because the sky model is different, but the spectral model is the same. And so let's see here. And so now what we're not going to change a lot of things in the fit. We're just going to tell to the fit run here that we have different data sets, and we're going to be fitting the model that was in each data set with Fermi and with magic here. And so this is, of course, a little bit longer to run than just Fermi or just magic, but here. So that was 6 seconds, that was not long. And so here we have the log parameter model, and you can see that there is only one log parameter model. We don't have alpha 1, beta 1, alpha 2, beta 2. And so this parameter is only applied to the Fermi data, and those parameters are common for Fermi and magic. Do you have question on this? It's a little bit, yeah, it's something that you need to pay attention. And one thing where we can check that it works is that now if you go above and you redisplay the models, yeah. So now you print the models, and you can see that the parameter here in Fermi 1.44 is the same as this one. So it's a way of checking that they were correctly fitted together. And these strange numbers that you see here is a random number that is generated to it's the name of the pointer or something like that. So you can see that here is the same as here. So this is telling you that those parameters are linked together. It is something that we have been working on between 1.3 and 2.0. We fixed some bugs. It's not perfect. And the way of tying parameters together, etc., is not easy. And hopefully this is something that we will improve in Gamma Pi in the future. And you may have noticed that at the beginning, before doing the fit, this strange name here did not appear, and it appears now only after the fit. Why? I don't know. It should appear from the beginning because it's tied on the object, but yeah, it's not clear to me exactly why this appears only after. But the best way of checking is that you print the model after and you check that the value are the same. So the parameters were tied. Okay, so now what we can do is any question on this before moving on?
Maybe the fitter link the parameters, and this is why the pointer appears after.
Yeah, you mean that they were fitted, the pointer, yeah, after the fit, yeah. Yeah, but if you use the same log par model at the beginning, then it should have known. I know that at some point there was a bug that we fixed in which if you had to do data sets, you had to do twice the printing, and it appeared after only the twice because the first printing method was generating the display. So they were clearly linked, but the label itself was generated at the first print, but after the print, something like that.
Okay.
But some things have been fixed. It seems that maybe not everything is fully So the other option is that you could maybe also do dataset magic models, something like crab, blah, 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 and then spectral model, and then say this equals maybe I haven't tried if this works, but maybe you can say, but it's probably easier to just create one model at the beginning and then assign the same object to different datasets. That's probably the simpler way. Okay, so now if we look at the errors here, you can see that the black curve here was fitted. So it was not fitted on the points here. The points are just for display. We will see later another example. But here the black curve fits well the data point all the way. You can see that adding the Fermi data points and also the magic data points might be slightly different, gives a slightly different best fit from the magic 2015 fit, especially at 100 GeV. But again, this is probably a different, the magic dataset that has been distributed that we use here, how different is it? Do you know from the 2015 paper?
I think the data are they were from the performance paper that was published in 2014. Maybe Julian remembers. I'm not
Sorry, can I
sure.
repeat this? The
What is the data set that we are using here are from the performance paper. But the magic collaboration results displayed with the log parabola was with 2015 data.
That's probably Roberta's paper, the one that has like a lot
Yeah.
of data inside. This
And-
crab spectral over 3 orders of magnitude.
Exactly, it's that one. And do they include the data from the performance paper?
Yes, yes.
Okay. So what we are using is actually a subset of what is of the data set that was used for the 2015 measurement.
Yeah. And again, here the fit is driven below 100 GeV by those green points going up, which is the pulsar contribution that we don't take into account. So, I mean, if you do a proper analysis, maybe you will remove some of the pulsar contribution in the off pulse, and the green point might go down a little bit, and maybe this goes back in agreement with the 2015 paper. But this is for illustrative purposes here, but you can see that it's very compatible anyway. So so it works. And what's interesting is that you can mix and match also. This is what I describe here, is that what we have done in Fermi is the 3D analysis. There is no other way in Fermi. You cannot do a 1D analysis because the PSF changes so much, and the galactic diffuse emission also changes a lot from one point to another. But for the magic analysis, I took the spectrum dataset on-off from the 1D analysis. We could also do the 3D with magic. But so that is what is interesting with those datasets is that the dataset can be a 1D object or a 3D object. And in the datasets here, you can have different types. We could even, for example, get the lasso data points. So of course, we don't have the lasso DL4, DL3 data, but if you get the SCD data point from lasso, it's not ideal, but of course, this is all you have. You can add the lasso data points here and do a combined fit in which it will be 3D analysis, 1D analysis, and flux points. So, I mean, depending on what you have access to, you could use that to do a really broadband coverage using. Best thing to do is have the DL3, DL4 data, but in case this is a collaboration where you don't have access, you're not a member, then you can use the flux point and combine, for example. Then what I wanted to show you is how different will that be if we do the less statistically correct way of doing the flux point. So we have in this notebook generated the flux point from Fermi, the flux point from magic, and you can create a data set. This is what I just said above, based on flux points. And so the flux point data set here, so we will load the data sets from the different flux points that we have generated before. In this case, we want to have a different log parabola model. So we recreate a new one. So otherwise, we want to compare the two solutions. And so here we will create a sky model in which we just have one spectral model. Of course, because we just have flux points, we don't need to have the spatial model that is defined because it's just flux points. And we don't have the background, etc. So because it's just a flux point. And this is the weakness of this is that you have no idea how well constrained is your background, your PSF, your redistribution matrix, etc. But we will try to play that game. Here again, we have some data sets that are made of flux points, so we can do this. We can do a fit. Now it's really fast because it's just using the flux point. There is no IRF convolution. And so we can compare, for example, those values here with the values that were obtained before. So 2.219 with 2.218. So you can see that it's, in that case, very similar. The beta parameter is 0.86, 0.84. So it's very slightly different. We will see how that propagates to the plots. So this is what we will do in that cell here. So here we use so if you have the spectral model, you can plot the butterfly here. And I have to say here that this is something that you don't see, but that is very new in GammaPy 2.0. We compared, so there were a lot of questions and issues raised on GitHub on GammaPy about the butterfly plots. And we realized that there is no simple way when you have large errors of propagating the errors and making something solid. The best way that we kept in the end was to do a sampling. If you have the covariance matrix, you can generate 100, 1000 samples following the covariance matrix and then do the envelope. And so this is the new implementation in the plot error function. So if you have something that is very steep or something that is very correlated, you can try with GammaPy 1.3 and GammaPy 2.0, and you will see that the butterfly will not be exactly the same. And so, for example, here you can see number of samples. So now this is the new way of plotting the errors in which you can see number of samples generated per parameter to estimate the error band. So it's rather fast. It's been generated 3,000 samples following the covariance matrix, and then plotting in memory everything and making the butterfly. And so what you see here is based that on all the samples. So we can do that for the joint likelihood and the flux points, and you can see that in this specific case, it's not a very big difference. You can see, however, that at high energy, that beta parameter that was slightly different makes a little bit of a difference. So it's not the best case. I'm not using the best case to sell you that the joint likelihood is better. But again, this is bright, this is the crab, and there is no upper limit. Probably we should try to find another case where if you have a non-detection or something like that, it will be much more constraining. Maybe if we try to fit an exponential cutoff power law or some things like that, it will make another difference. But at least the idea here of that notebook was to show you, of course, for most of the science that we do, Fermi and Cherenkov telescopes are is the perfect combo. And therefore, I think these notebooks really summarize, if you have to do one thing, is Fermi plus some Cherenkov telescope. And here you have the two recipes of how to do it. It might be that for your given source, only Veritas has published the relevant data points, and you need to work with the flux point. And in that case, you can combine Fermi with Veritas or etc. So, I mean, in an ideal world, you only want to do joint likelihood fit. Sometimes you don't have access to the raw data, and so you have to live with that. And in particular, I think it's interesting to try to play that game, Fermi, atmospheric telescope, and then water Cherenkov or KM2A from Lasso and to see how their data point might constrain the cut, etc., doing really the fit from MEV to PEV with that method. Yeah, and so that's mostly it for that notebook. Do you have questions? Did that work for you? Did you get some similar results on the butterfly plot or? Has anyone encountered some error in the notebook or did that all worked okay?
Were you able to find the stacked spectra from
Yeah.
yesterday? I hope so. I hope that it went.
Well, anyway, you can play with it again. And so yeah, if you also now, the good thing is that you have an example of what a FermiPy configuration looks like. So if you install FermiPy, you can define this and you can redo your own analysis and go more in detail, etc. Or use that for another source, and you can do that kind of notebook then for your other source that you're working on. But the good thing is that really now with some bug fix, performance improvement, and that helper function, uh, playing with Fermi data and GammaPy has become even more convenient. I haven't tested yet to go to very low energy. The problem with very low energy is that you need to make a region because of the PSF that is much bigger, which means that if you are in the galactic plane, you can get 50 or maybe 100 sources. And then I don't know if you will start encountering memory limits but this is something that if you have a case, please explore and let me know. I will be happy to have some beta testers on this.
Just a curiosity on the paper with Mireia, if I may, Fabio. So did she produce the, let's say, low energy data in a format compatible with GammaPy, with the OGIP standards, or the instruments already had some data in this format?
No, she produced well, if you go to Swift, then you have the Swift science tools, and then you can produce a spectrum, the PHA, IRF, and RMF files that you read in XSpec. Those files can be read in GammaPy now. So you can read PHA, IRF, RMF, and make it as a spectrum dataset on off, like the 1D similar. So the thing that was more complicated and a bit more tricky, but it worked at least for some cases, was to do UV. So Swift UVOT. That Swift UVOT can produce PHA, so that was okay. But then Liverpool telescope. Liverpool telescope, then it's a bit different, the way of processing it. And this was more by hand to do the things. But otherwise, if you stay within X-ray OGIP products, then it's rather straightforward to load them in GammaPy. If you want to do the 1D analysis, the 3D, then there are some problems. But the 1D analysis for now really works, in which you can really do, and the real power of it is that here we plotted a log parabola model, but if you have X-rays, especially in the case of the Blazar where X-rays were in the rising part, then you can really fit the inverse Compton model, and you can go to NIMA. I mean, this is really a step forward comparing to going to XSpec, plotting, fitting a power law, going to Fermi, fitting a power law, going to Cherenkov, fitting a power law. Here you do full forward modding of a physical inverse Compton model. That's really two steps that are interesting. So yeah, all of this is still experimental. We done the test. It gives similar results, but of course it's not. If you test it and see something strange, don't hesitate to report it.
Any other question or curiosity? Okay, if not, thanks again for joining, Fabio, and for preparing the notebooks.
Yeah, thank you.
And I think that concludes the school, basically. So I hope it was interesting. I hope, yeah, you learned something useful. And I remember that the data that we prepared for the school are free to use. So you have CRAB, Markarian, 1ES1218, and Geminga. As I said at the beginning, you can use them for scientific analysis. The only thing that we request from you is to contact the collaboration first, because there is a couple of publication in preparation with this data. But hopefully, yeah, you can make use of them and you have acquired some skills with the school.
How
So
many hours of observation in the crab does that correspond to?
so the crab is just a subset of the one that we released with the DL3 paper. When we did the validation paper, I think we released 40 or 60 hours of the crab. Let me check. So when we did the magic DL3. So this is the data release that we did when we did the validation paper. And I think this is 60 hours of the crab. And you have the crab also a different offset. And for the school, we just used the crab at 0.4 offset. Let's say we used a subset of this. And then in the school, yeah, in the data that people have used for the school, we have added basically two blazers and Geminga. And this is quite a lot of data because Geminga is 2 years of data taking. So I think it's tens of hours for sure. And Markarian as well, because it's a week in April, but it was really densely sampled. So there's quite a lot of data. Okay, that's it. If you have any question, you can contact us on the email of the school, or you can contact me personally. So thanks a lot for joining and take care. See you. Bye bye.